Okay, hello again, Ms. Scott, to explain energy. Now, when we started our quarantine unit, we started off exploring thermal energy, and I want to kind of give an overview of that because weren't able to finish the unit, but we did learn a lot about it. But before we get into that, I want to make sure that you understand that there are many different types of energy and what those types of energy actually are. um, just as a matter of, uh, you know, putting, uh, give, what is it? Giving people their due. A lot of the information I'm going to be giving to you tonight is out of this book right here, Everything You Need to Ace Science in One Big Fat Notebook. It's a really, really good book. Any middle school parents out there, these books, there are 5 of them in a series. They cover science, ELA, world history, American history, and math. Here we go. And they're really, really good to help kind of clarify certain things because a lot of times, like math books will talk in a language that that 6th graders that can't necessarily grasp or connect to. But these books do really, really, really good work. So anyway, we're going to look at forms of energy, and then I'm going to go back into thermal energy because again, we didn't finish our unit. I really want you to make sure that you have a good overall uh, grasp of the topic. Okay, so here we go. You see I have my little board here. So we'll pull that up. And we are talking about, as it says, forms of energy. See how pretty I made that? We're going to talk first about conservation of energy. And first, we're going to back it up and talk about energy itself. Energy is a property of matter. What is matter? What is this? Well, matter is everything. It's everything that has mass and takes up space. So mass is kind of like the weight that matter occupies. And so anything that has mass and takes up space is matter. And energy is a property of matter. And we're going to talk about the conservation of energy. So energy is a property of matter, and it comes in many forms, such as heat, sound, light, and motion. Energy, like matter, is always conserved. What does that mean? When we conserve something, we save it for later use. The amount of energy in a system remains the same, although it may change forms and be transferred between objects. So we're going to talk about different types of energy and how those types of energy transform depending on how they're used. We're not creating energy, we're not dissipating energy or getting rid of energy, we're changing energy. So, for example, when a golfer strikes a ball, the energy from his or her swing is transferred to the ball, which then, goes flying and hopefully lands in a hole. So the law of conservation of energy states that energy can neither be created nor destroyed. Okay, so when we are hitting that ball, we are not creating energy. We are taking the energy from our body, using the club, putting our energy into the club, and transferring that energy that we put into the club into the ball. So it changed. It transferred, but it was not created and it was not destroyed. An example of energy transformation is light energy from the sun being absorbed by plant leaves to grow and thrive. The energy produced in the plant leaves is transferred to energy in our bodies when we eat our veggies. When we eat our veggies, eat your veggies. When we run or move, we release the stored chemical energy into mechanical energy. So technically, we're solar powered. Okay, so two of the more familiar forms of energy that you guys are going to hear about as you go through all of your science classes and in 7th, 8th, and into high school are potential energy and kinetic energy. So let me erase this. Oh, that pen's going to stain my board too. This is about the blues and greens. I want to stain my board. So we have potential and we have kinetic. So it's showing up not really well. It's okay, you can see it well enough. Okay, so if you were to drop a pen, okay, let's say we have a pen that's right here in my hand. And when my hand loses enough energy to hold it here, the pen will fall. Here we go, the pen is right here. And when my hand gets tired, the pen will fall. Now, right now, it has no energy that is actually discernible. It does not have any kinetic energy. It's not moving on its own. It's not doing anything, blah, blah, blah. It's just kind of sitting there. But because it has all this space between here and here that can be occupied by gravity. When my hand stops being able to hold that pen because it's getting so tired and heavy, and I can't do it anymore, and it falls, it has utilized its potential energy. So when it was up here, it had energy that was possible, energy that could be disseminated from this pen, and that was potential energy. And it was converted as it fell into kinetic energy. So the energy of its movement was kinetic energy. So both of these are mechanical energies, which is the energy of an object based on its motion or position. For example, when you kick a ball up a hill, it has kinetic energy as it's going up the hill. And if it stays there on top of the hill, but just almost on the edge of it, it has potential energy. And as it slows and stops, the energy of motion is transferred to the potential energy in the ball's position. The potential energy of the ball can quickly be converted back to kinetic energy when the ball rolls back down that hill. It gets transferred between potential and kinetic forms, so energy is conserved. It was not created, it was not destroyed, it was transferred. Okay? So that type of energy where the ball is on the edge and the pen is up here, that's gravitational potential energy, because it has the potential to release energy, not destroy it, release it, release the energy by using gravity. Okay, kinetic energy can be transferred to other objects through collisions. Think of bumper cars. When one car bumps into another, it transfers its energy, causing the other car to move. It's kind of like dominoes, no? Where you have a bunch of dominoes that are sitting up and one of them tips over, and all that energy when it's standing up, it's kinetic, it's a potential energy. Then when it falls down, it turns into kinetic energy, and all that potential energy of the standing up dominoes gets transferred into kinetic energy when it all falls through collisions. The amount of kinetic energy an object has depends on both its mass, its weight, and weight per size, and its velocity, how fast it's going. More mass and more velocity means more energy. The amount of potential energy depends on both the mass and the height of the object. More mass and or more height means more energy. Okay, so that's just a small overview of kinetic and potential. And you guys are going to get a lot more of this as you get into high school. But I wanted to let you know that when we're talking about energy, we have to be very specific about what it is we mean by that, okay? Because there are all kinds of different types of energy. There's different kinds of, even under these two banners of potential and kinetic. Under potential, there's gravitational potential energy or mechanical potential energy. There's also elastic energy. Take a rubber band and you pull it back. You use your energy of your hand, transfer it into this rubber band and you pull it back. Now that's potential energy until it's released. That's elastic energy. Under kinetic energies, there's mechanical kinetic energy, which has to do with moving objects, thermal energy, which is what we're going to be looking at, electromagnetic energy, which is light waves, both visible and invisible, sound energy, which is molecules bumping into each other to transmit sound, and electric energy, which is the flow of electrons. There are other types of energies that you're only going to hear about probably in high school, maybe college, probably college. Nuclear energy and nuclear fission and chemical energy. Okay, so onward now to thermal energy. So you guys did a couple of things in this science unit that talked about thermal energy that led you to coming to certain conclusions about thermal energy. So let me put this up here. Thermal energy. That's what we're going to be talking about. And the primary way of measuring thermal energy is through temperature. Remember, the temperature is the measurement of how hot or cold something is. How hot or cold something is. So the actual, this is what we have come to think of as temperature, how hot or cold something is, but the actual scientific definition of temperature is the average kinetic, or the energy that's trapped, ready to use, but, oh wait, no, the energy that's actually being used at the time, average kinetic energy of molecules in a substance. So remember we did that little thing where you had that box with all of the dots in it and how fast they were moving according to how hot or cold it was. So that was the scientific way of actually measuring how hot or cold or something is how fast those molecules are moving inside that area or in a substance. So the molecules in either a liquid, solid, or a vapor are always in motion. These molecules move around and bump into each other. And because the molecules are moving, they have kinetic energy. They are moving. They have movement. And the faster the molecules move, the more kinetic energy they have. If you compare the molecules in a cup of hot cocoa to the molecules in a glass of cold chocolate milk, the hot cocoa molecules will be zipping around much faster than the cold chocolate milk molecules. Now I did that experiment and hopefully you watched it or even did it yourself, where we put the dye into hot water and the dye into cold water and saw how fast how much faster it dissipated into the water versus how much slower it did in the cold water. Okay, onward. So in order to measure temperature, we use things like a thermometer, therm. thermometer. So usually when things heat up, they expand. And when things cool down, they contract. Expand, contract. Thermometers are based on the expansion or contraction of material according to the temperature. So the material that's actually found inside of the thermometer is usually mercury, and that will expand and contract according to whether it's hot or cold, but also the glass that holds the thermometer will expand and contract. So even if the substance inside does not respond to the heat or the cold, the expansion or contraction of the glass that holds it may actually push the thermometer's reading up simply because it's squeezing the substance inside. When something is at a higher temperature, the liquid contained in the thermometer expands and indicates a higher temperature. So converting temperatures, we usually measure temperature either in Celsius, which is a metric scale, or in Fahrenheit. That's the English scale that it's fairly obsolete. Almost anybody anymore that is, especially in science, they use Celsius. You can convert between Celsius and Fahrenheit with formulas that I'm not going to go over right now because they're not important to actually knowing about all of this. Scientists will sometimes use Kelvin scale, which is the SI unit for temperature. So you convert between Celsius and Kelvin, we use a different formula. So we're talking about 3 different forms of measuring temperature. I'll tell you how I calculate the differences in temperatures, and that is my good old iPhone. So watch this. I'm going to go to my thing here, and we'll put in here temperature conversions. And you can see right there, well, you can't see because of the thing. It's like really all blurry. I guess I could, but I'm not going to. You put in your temperature. So if you have, you can see right, well, let me do this, where it's not going to be blurry. So you can see on there, it says temperature of at 32 degrees Fahrenheit, 0 Celsius. That's because those are equal temperatures. 32 degrees Fahrenheit is freezing in Fahrenheit, and 0 degrees Celsius is freezing in Celsius. So now if we wanted to say like today was 107 degrees, we're going to put that in here, 107 degrees Fahrenheit. And it's going to tell you that in Celsius, that's 41.6667 degrees Fahrenheit, or Celsius. Duh. Okay, so you can see how it converts like that. You can also find on your iPhone or on whatever other thing how to convert either of these 2 temperatures into Kelvin. It's a bigger scale. Fahrenheit is, I wish we would just stop using it altogether because it really doesn't make any sense. Celsius is super easy because at 0 degrees Celsius, water freezes. At 100 degrees Celsius, water boils. In Fahrenheit, it's 32 degrees to freeze, and I believe it's 112 to boil. That's crazy. It might be 212. I have to figure out. More technology. Alexa, at what temperature Fahrenheit does water boil?
Water boils when it reaches 212 degrees Fahrenheit or 100 degrees Celsius. The amount of time it takes for this to occur varies depending on how much water you're boiling, whether or not there's a lid over the water, the temperature of the pot, lid, and stove, the water's salinity, the altitude, And the pot surface area,
Alexa, stop.
volume.
212 degrees Fahrenheit is when water boils. So, I mean, it's a little bit crazier. Nothing is very, like our temperature, our body temperature, our core temperature is usually about 98.6, give or take a degree. 98.6, it's a little bit difficult to calculate. I'm not really sure what that, hey, look at this. What that calculates out to in Celsius. Let's see here. 98.6 is 37 degrees. Isn't it easier to say 37 degrees Celsius? My body temperature is 37 degrees Celsius, not 98.6. I think Celsius is a much easier scale to use. Anyway, with thermal energy, let's go back to the board, shall we? Well, let's just stay here for a minute. The total amount of kinetic and potential energies in the molecules of a substance is its thermal energy. Let me read that again. The total amount of kinetic and potential energies in the molecules of a substance is its thermal energy. The difference between temperature and thermal energy is that temperature is the average kinetic energy of molecules in the substance, and thermal energy is the sum of the kinetic and potential energy of all the molecules of the substance. Wow. Okay, the difference between temperature and thermal energy is that temperature is the average kinetic energy of molecules of the substance. So temperature, you're only measuring the kinetic energy. But when you're calculating thermal energy, you're using both kinetic and potential energies as an average. Add them together and average it out. Whew. Awesome. Okay. For example, a single brick has less thermal energy than a stack of bricks because it has less potential energy. But the single brick and stack of bricks may have the same temperature. So when we feel that something is hot, it's because the object is warmer than our hand. I think that's pretty self-explanatory. The transfer of thermal energy from warmer to cooler objects is called heat. Heat is technically the transfer of thermal energy from a warmer substance to a cooler one. Thermal energy always moves from high to low energy. So when you feel temperatures, if you can imagine this, where you take a big pot of water that's hot and you put it into a big tub of water that's cold, it's not the cold water that's making the water warm, it's the hot water that's making the water warm. It's the mixture of the hot water going into the cold that does all the work. Think about that for a minute. So thermal energy always moves from high to low energy, or in other words, from warmer to cooler objects. Thermal energy continues to transfer between substances until both are at the same temperature. So thermal transfers can occur through a couple of different things. And I'm going to write this down because I think this is very important. So let me put this on the board real quick. So thermal transfer can occur through conduction, through radiation, or through convection. Thermal transfer can occur through conduction, radiation, or convection. Conduction is the transfer of heat from a warmer object to a cooler object through direct contact. So if you have very, very cold hands, and I take your cold hands into my warm hands and I go like that, That is conduction. The molecules in the warmer object collide with the slower moving molecules in the colder object, transferring energy. For example, touching a hot stove with your hand will hurt. Don't do it. Radiation is the transfer of heat through electromagnetic rays. And I bet you didn't know that that happened, did you? Electromagnetic rays. For example, the sun hitting the earth or the warmth you feel when you sit next to a fire. So, I mean, the sun's not touching you. It's just throwing out all this heat. And generally speaking, most of the heat that you feel is not actually directly from the sun. It's from the air around you that is heated up and then on you. Convection, the transfer of heat through the movement of a fluid such as air or water. Wait a second, fluid such as air? Yeah, because of water vapor. There's lots of water in our air, and it transfers heat energy. The transfer of heat through the movement of a fluid, such as air or water. Air in your home moves in convection currents. The warm air from a heater rises, cools down, then sinks back down to the floor. You can enhance the flow of air convection with a ceiling fan. I do that all the time. Okay, so basically, that is our overview of thermal energy. Things that I want you to remember are these three things: the conduction, radiation, and convection, and what those three things mean. I want you to remember that heat is the transfer of thermal energy from warmer to cooler objects. And I want you to remember that you could probably do yourself a great deal of service by learning how to tell temperature using Celsius. It's time. We've got to get to the metrics, guys. It's just better. All right, so that's my overview of thermal energy, and I hope you learned something. And yeah, okay, I'll talk to you later. Bye. No, stop. Okay, now bye for real.